So in this video, we're going to ask how pyruvate enters the citric acid cycle. This is a connection between the glucose network, which we've been talking about, right? Pyruvate's the output of glycolysis, and where we're going, which is going to be a bunch of acetyl-CoA centered reactions. And today we're asking basically how do those connect to each other? So how does pyruvate enter the citric acid cycle? Call that our big question. So hopefully you've seen this before. You remember seeing this. This is our map of central carbon metabolism. And to this point, we've been focusing over here on stuff that's going on here with glucose and pyruvate and the pentose phosphate network and all those things happening. And we're headed over here to study a bunch of reactions and pathways on this side, this acetyl-CoA network. And the thing we're going to be talking about today is pyruvate connecting these two to each other. Pyruvate is going to let us go from this glucose-centered network to this acetyl-CoA-centered network. And if we zoom across all of the acetyl-CoA network reactions or pathways that we're going to talk about, what you can see is we've got a bunch of different pathways that are happening that do beta oxidation, releasing energy or exporting energy, all these things, but all of them are centered around acetyl-CoA. And today we're just focusing on how do you go into acetyl-CoA starting with pyruvate to launch into the rest of these pathways. So with those preliminaries, let's take a step back and say, let's think about the process we've done thus far with glucose. So what we've done thus far with glucose is we've taken glucose, and if we run all the way through fermentation, we end up with 2 lactate molecules. What we've effectively done is cut a glucose in half. There's the same number of carbons, the same number of oxygens and hydrogens and electrons. It's just we've rearranged them. One way to see this is by looking at the total oxidation number of these molecules, right? So if you look at glucose, you see that it has an oxidation number of -1 here, 0 is at the rest of the molecule, and then a +1 over here. Total oxidation number is thus 0. And if you go over to lactate, what you see is it's a -3, a +3, and a 0, so again, a 0. We've rearranged things for sure, and we've used that to extract energy, but we haven't changed the actual oxidation number. We haven't done a full redox reaction if you just do glycolysis plus fermentation. If we can do a redox reaction, we're going to get a lot more energetic bang for the buck. So what I'm doing here is I'm comparing glucose going to 2 lactates in terms of heats of combustion change. So if you light these molecules on fire and ask how much energy is released, the difference between glucose and lactate is 16 kilojoules per mole per carbon. Whereas if you can take a lactate and burn it with oxygen to carbon dioxide, you can release 454 kilojoules per mole per carbon. So way, way, way more energy is available if you can do this oxygen reaction rather than stopping with glucose going to pyruvate, glucose going to lactate. So how do we do this? Well, what we can do is take a lactate, as I'm drawing it here, can turn that into 3 carbon dioxides. Take those 3 carbon dioxides, and in that process of making the 3 carbon dioxides, you can reduce some electron carriers. So 5 NAD pluses to 5 NADHs, and then this molecule Q, ubiquinone, going to ubiquinol, which is also going to take some electrons. You then take those electrons and you pass them off onto water. So onto water. You choose molecular oxygen to oxidize the, say, NADH to NAD+, reducing it to water, and this process is energetically favorable. And if you look at net, what we do is these molecules are sort of just currencies, they're just being passed back and forth. So the overall reaction ends up being lactate plus oxygen gives us carbon dioxide and water. We're doing that respiration reaction. We're just doing a bunch of steps in the middle. And what we're going to be doing in the rest of this video is talking about the first step along this pathway. Okay, so I've been using lactate as my example, and then we're going to start talking about pyruvate. So just to make sure we're on the same page with this, I'm going to make myself disappear for the moment. We have this reaction, which I showed, which is this is lactate fermentation, right? You can take a pyruvate and an NADH, and then you can interconvert them to make a lactate and an NAD+. This is how we get fermentation going, and we recycle NAD+ after when we're running glycolysis. But this reaction can actually run both ways. If I build up a high enough concentration of NAD+ or a high enough concentration of lactate, this reaction can start going backwards. And so a lactate can be, we can think about it as a lactate can generate an NADH, a reduced electron carrier, and make pyruvate, allowing that to go forward. So the fermentation reaction, I don't know if I said during the actual video on that, is actually reversible. You can go backwards and you can go forward depending on the concentrations of things. So that's why we're going to be talking about pyruvate as the input into the next step, because pyruvate can either be generated from lactate or it can be generated directly from glycolysis and then passed in to do this. Let's make lots of energy by doing the oxygen reaction things inside of the acetyl-CoA network. All right, so we are now going to start connecting these molecules into this acetyl-CoA network. Acetyl-CoA network is built around this molecule coenzyme A, or CoA. Shown here, it's got this big complicated structure that we don't actually have to worry very much about, because the purpose of this structure is to be recognized as a handle by enzymes. So this is for recognition and for moving things around and for solubility. But we don't actually, there's no chemical rearrangements that are happening once we've made coenzyme A. Coenzyme A is just kind of like an ATP. There's this big handle to move around phosphates, or an NADH, there's a big handle to move around electrons. Coenzyme A, there's a big handle to move around stuff over here. And this stuff over there can, for example, be an acetyl group. So this acetyl group is glued onto the end of the CoA, making acetyl-CoA. And I've said it a bunch of times already, but I'm going to say it again. This is the center of the acetyl-CoA network. Oh, look, I have a picture of it. This is the center of the acetyl-CoA network, right in the center. All of the different pathways connect to this one molecule. Okay, so how do we make acetyl-CoA from pyruvate? So the way that this works is we take a pyruvate up here, and we're going to take the carboxylic acid here, or carboxylate as I've drawn it, and turn it into a carbon dioxide. In the process of turning that into a carbon dioxide, we are going to reduce an NAD+, which I'm just not showing all of the rest of it hanging off there in the R group, but this is an NAD+ molecule, and we're making it into an NADH. And in that process, we also take the acetyl group and we glue it onto the end of the CoA to make our acetyl-CoA here. So this is showing the CoA part, and this is the acetyl part. So we made acetyl-CoA. This is all catalyzed by the enzyme pyruvate dehydrogenase. This reaction, as it turns out, is highly favorable. You release 33 kilojoules per mole when you do it. So if we had to bet, we would have a strong bet that it's going to go forward, not backwards. And what this means is actually that the carbons that go from pyruvate onto acetyl-CoA are now irreversibly committed to being inside of the acetyl-CoA network. They're not going backwards, right? You do this, now you're stuck either running the citric acid cycle or running fatty acid synthesis or something. You can't actually take those and go backwards into, say, make glucose. The way this reaction works, if we start breaking it apart and teasing it apart a little bit, is you have a very favorable oxidation reaction shown here. So you're basically doing this decarboxylation and you're oxidizing this carbon. And in the process of that oxidation reaction, you reduce the NADH, the NAD plus to NADH. That yields minus 65 kilojoules per mole. So this is like a seriously favorable reaction. I'm going to hide again. But you couple this to an unfavorable dehydration reaction. And that dehydration reaction is taking the acetyl group, it's now you've made an acetate through this reduction reaction, this oxidation reduction reaction. You pop off of water, and now you glue it onto the CoA to make acetyl-CoA. That is unfavorable by 31 kilojoules per mole. But as last I checked, minus 65 plus 31 is still a very negative number. Minus 33 still, because so there's still a lot of energy to drive this reaction forward, even though you're actually coupling an unfavorable reaction and a favorable reaction under the hood. You're probably thinking, or hopefully you're thinking, I've sort of seen something like this before, and we've actually have seen something like this in glycolysis. Remember the enzyme glyceraldehyde dehydrogenase? It actually does something very similar. It takes an NAD+, and it takes a central carbon intermediate. It does an oxidation reaction on that. You'll notice you go from an aldehyde here to a carboxylate here, so that is more oxidized. That is favorable by minus 60 kilojoules per mole. But it couples this favorable redox reaction to a very unfavorable phosphorylation. So it takes an inorganic phosphate from the environment, sticks it on here, making this 1,3-bisphosphoglycerate here. So net the reaction is about 0 kilojoules per mole, or minus 1 kilojoules per mole. But it's achieved by coupling this very favorable redox reaction to this very unfavorable phosphorylation reaction. And what we're seeing is the exact same thing here. What we've done is we've taken that redox reaction and we've actually paid some energy to prime an acetyl-CoA. And this is one of the superpowers of an acetyl-CoA, actually, is now I'm drawing the reaction in the opposite direction. If I take this acetyl group and I chop it off, releasing the acetate, that's going to give me minus 31 kilojoules per mole, which means that this molecule is just ready to go. So if we want to say stick that acetyl group onto something, we already have some driving force available, which is actually, I think, part of the reason that our cells are so addicted to acetyl-CoA is it not only carries around carbons to move around, but also provides the energy packet that you need to stick those carbons onto something or to do something with them. And so the model here to think about is this is just like ATP, right? ATP is primed to donate its inorganic phosphate. You get minus 31 kilojoules per mole for donating that phosphate. You get about minus 31 kilojoules per mole for chopping off this acetate. So it's got a similar energetic kick to, say, an ATP molecule. Okay, that's actually all I'm going to say now about this. We've taken carbons from pyruvate and thus from glucose, and we've now made them into acetyl-CoA. Now that they're acetyl-CoA, they can go on and do all the cool things in the acetyl-CoA network. The energy for this process comes from a decarboxylation reaction, from chopping off that, releasing of carbon dioxide, making this an irreversible step that's committing our carbons from pyruvate into doing reactions inside of the acetyl-CoA network. But then also, by doing this reaction in this way, we've primed the molecule to do further chemistry. And that's what we're going to start exploring later, is all the cool chemistry that you can do once you've built an acetyl-CoA. Okay, so that's what I got. Hopefully that's a helpful introduction to how to think about pyruvate going to acetyl-CoA. Next videos, we're going to talk about the citric acid cycle and all the stuff that happens once you've built acetyl-CoA. So I look forward to talking to you then.